Dot product. Now that we can add, subtract, and scale vectors, you might be wondering whether we can multiply vectors. It turns out there are two different ways to multiply vectors, one which results in a number and one which results in a vector. In this section, we'll focus on the first, called the dot product or scalar product, since it produces a single numeric value, a scalar. We'll begin with some motivation. In physics, we often want to know how much of a force is acting in the direction of motion. To determine this, we need to know the angle between direction of force and the direction of motion. Likewise, in computer graphics, the lighting system determines how bright a triangle on the object should be based on the angle between object and the direction of the light. In both applications, we're interested in the angle between the vectors, so let's start there. Suppose we have two vectors. Vector A equals components A1, A2, and vector B equals components B1, B2. Using our polar coordinate conversions, we could write vector A equals components absolute value of vector A cosine of alpha and absolute value of vector A sine of alpha, and vector B equals components absolute value of vector B cosine of beta and absolute value of vector B sine of beta. Now, if we knew the angles alpha and beta, we wouldn't have much work to do. The angle between the vectors would be theta equals alpha minus beta. While we certainly could use some inverse tangents to find the two angles, it would be great if we could find a way to determine the angle between the vector just from the vector components. To help us manipulate theta equals alpha minus beta, we might try introducing a trigonometric function. Cosine of theta equals cosine of alpha minus beta. Now we can apply the difference of angles identity. Cosine of theta equals cosine of alpha multiplied by cosine of beta plus sine of alpha multiplied by sine of beta. Now A1 equals the absolute value of vector A cosine of alpha. So cosine of alpha equals A1 divided by the absolute value of vector A. And likewise, for the other three components, making those substitutions, cosine of theta equals A1 divided by the absolute value of A multiplied by B1 divided by the absolute value of vector B plus A2 divided by the absolute value of vector A multiplied by B2 divided by the absolute value of vector B equals A1 B1 plus A2 B2 divided by the absolute value of vector A multiplied by the absolute value of vector B. Absolute value of vector A multiplied by the absolute value of vector B cosine of theta equals A1 B1 plus A2 B2. Notice the expression on the right is a very simple calculation based on the components of the vectors. It comes up so frequently, we define it to be the dot product of the two vectors notated by a dot. This gives us two definitions of the dot product. Definitions of the dot product. Component definition. Vector A multiplied by vector B equals A1 B1 plus A2 B2. Geometric definition. Vector A multiplied by vector B equals the absolute value of vector A multiplied by the absolute value of vector B cosine of theta. The first definition, vector A multiplied by vector B equals A1 B1 plus A2 B2, gives us a simple way to calculate the dot product from components. The second definition, vector A multiplied by vector B equals the absolute value of vector A multiplied by the absolute value of vector B cosine of theta, gives us a geometric interpretation of the dot product and gives us a way to find the angle between two vectors as we desired. Example 1, find the dot product of components 3, -2 multiplied by 5, 1. Using the first definition, we can calculate the dot product by multiplying the x components and adding that to the product of the y components. Components 3, -2 multiplied by components 5, 1 equals 3 multiplied by 5 plus negative 2 multiplied by 1 equals 15 minus 2 equals 13. Example 2. Find the dot product of the two vectors shown. We can immediately see that the magnitudes of the two vectors are 7 and 6. We can quickly calculate that the angle between the vectors is 150 degrees. Using the geometric definition of the dot product, vector A multiplied by vector B equals the absolute value of vector A multiplied by the absolute value of vector B cosine of theta equals 6 multiplied by 7 cosine of 150 degrees equals 42 multiplied by the negative square root of 3 divided by 2 equals negative 21 multiplied by the square root of 3. Now we can return to our goal of finding the angle between vectors. Example 3. An object is being pulled up a ramp in the direction components 5, 1 by a rope pulling in the direction component 4, 2. What is the angle between the rope and the ramp? Using the component form, we can easily calculate the dot product. Vector A multiplied by vector B equals component 5, 1 multiplied by component 4, 2 equals 5 multiplied by 4 plus 1 multiplied by 2 equals 20 plus 2 equals 22. We can also calculate the magnitude of each vector. Absolute value of vector A equals the square root of 5 squared plus 1 squared equals the square root of 26. Absolute value of vector B equals the square root of 4 squared plus 2 squared equals the square root of 20. Substituting these values into the geometric definition, we can solve for the angle between the vectors. Vector A multiplied by vector B equals the absolute value of vector A multiplied by the absolute value of vector B cosine of theta. Theta equals cosine inverse of 22 divided by square root of 26 multiplied by the square root of 20, which is approximately 15.255 degrees. Example 4. Calculate the angle between the vectors component 6, 4 and component negative 2, 3. Calculating the dot product, component 6, 4 multiplied by component negative 2, 3 equals 6 multiplied by negative 2 plus 4 multiplied by 3 equals negative 12 plus 12 equals 0. We don't even need to calculate the magnitudes in this case since the dot product is 0. With the dot product equaling 0, as in the last example, the angle between the vectors will always be 90 degrees, indicating that the vectors are orthogonal, or more general way of saying perpendicular. This gives us a quick way to check if vectors are orthogonal. Also, if the dot product is positive, then the inside of the inverse cosine will be positive, giving an angle less than 90 degrees. A negative dot product will then lead to an angle larger than 90 degrees. Sign of the dot product. If the dot product is 0, the vectors are orthogonal, perpendicular. If the dot product is positive, the angle between the vectors is less than 90 degrees. If the dot product is negative, the angle between the vectors is greater than 90 degrees. Projections. In addition to finding the angle between vectors, sometimes we want to know how much one vector points in the direction of another. For example, when pulling an object up a ramp, we might want to know how much of the force is exerted in the direction of motion. To determine this, we can use the idea of a projection. In the picture above, vector u is a projection of vector A onto vector B. In other words, it is the portion of vector A that points in the same direction as vector B. To find the length of vector u, we can notice that it is one side of a right triangle. If we define theta to be the angle between vector A and vector u, then cosine theta equals the absolute value of vector u divided by the absolute value of vector A. So the absolute value of vector A cosine of theta equals the absolute value of vector u. While we could find the angle between the vectors to determine this magnitude, we can skip some steps by using the dot product directly. Since vector A multiplied by vector B equals the absolute value of vector A multiplied by the absolute value of vector B cosine of theta, the absolute value of vector A cosine of theta equals vector A multiplied by vector B divided by the absolute value of vector B. Using this, we can rewrite the absolute value of vector u equals absolute value of vector A cosine of theta as the absolute value of vector u equals vector A multiplied by vector B divided by the absolute value of vector B. This gives us the length of the projection, sometimes denoted as the composition base vector B of vector A, equals the absolute value of vector u equals vector A multiplied by vector B divided by the absolute value of vector B. To find the vector u itself, we could first scale vector B to a unit vector with length 1 to vector B divided by the absolute value of vector B. Multiplying this by the length of the projection will give a vector in the direction of vector B, but with the correct length. Projection base vector B of vector A equals the absolute value of vector u multiplied by vector B divided by the absolute value of vector u equals vector A multiplied by vector B divided by the absolute value of vector B multiplied by vector B divided by the absolute value of vector B equals vector A multiplied by vector B divided by the absolute value of vector B squared multiplied by the vector B. Projection vector. The projection of vector A onto vector B is projection base vector B of vector A equals vector A multiplied by vector B divided by the absolute value of vector B squared multiplied by vector B. The magnitude of the projection is component base vector B of vector A equals vector A multiplied by vector B divided by the absolute value of vector B.